All right, thanks for coming. So this is going to be a very easy talk for a Sunday morning, right? Especially post-hangover, I guess. All right, so thank you for coming. So today we talk about neural network, right? We know that computer can calculate complex numerical computation like in a blink of an eye. They're very fast, right? And they probably have more power than human brain. However, still today, brain outperform computer in almost every aspect, especially decisional. What artificial intelligence want to achieve is to make computer be able to make a self-decision. And one of the tools that artificial intelligence use is neural network. So let's talk about neural network. Oh, okay. So this is the agenda. You see in the back, maybe you want to come over? Okay. So we talk about neural network and a little bit what it does, what kind of problem solve, and how does it work? Because we're going to try to implement, I implement the neural network in two different ways, right? In fact, I'm going to show a little bit of code. However, framework code is not important here. What's important are concepts. Can be applied in different kind of programming languages. And by the way, all the slides and code are on GitHub. In the hand, I have my link you can download eventually to take a look home. But so we're going to implement neural network in a few different ways using the actor model, functional programming, see the pros and cons. And hopefully with time, I try to rush through to have some good demo in the end. If you have any question, just yell at me right away. I'd rather answer in the context rather than wait in the end. So the main takeaway, really, that neural network is to solve complex machine learning problem, and that it turned out that neural network is based on overall simple concept, like simple math, like linear algebra, and that that's actually my background. I do a lot of work in parallel computation, distributed system. It turned out that I was very happy to discover that neural network can be easily parallelized. Actually, there is this term about embarrassingly parallel, which is nothing to be ashamed about it, but it refers to some sort of algorithm that is easier to divide in subset and parallelize easily. Okay, the bonus slide about me. My accent is from Italy. I moved here 10 years ago. I live in DC, but I'm going to move in Charlotte, North Carolina next month. So I'll be with neighbors, right? I work with different kind of technology stack, very passionate about functional programming, and recently I published a book about functional concurrency. This is my detailed information, but this probably is not the right color for this room. But fortunately, this is the only purple slide you're going to see. So, but I want to know about you. How many of you are familiar with machine learning? Okay, so just one, so I can tell whenever I want today. All right. So, well, I guess nobody familiar with neural network? That's what. Okay, this is actually great because the first half of the talk really bring up to speed from the 0 to 100 how neural network works and how you could implement it. How many of you are familiar with the actor model, maybe, or agent? All right, I'm gonna touch base about that as well. And functional programming. All right, it's very heavy. Raise the hand today. Okay, I guess. So motivation. I don't have a machine learning background, but I've been exposed to machine learning several times at work. I built a recommendation engine using neural network for e-commerce, and I built natural language processing also using neural network. And during my experience in machine learning, I was fascinated how really magically the neural network construct work and predict values, especially like in forecast and finance, right? That pretty much quite used. And neural network is not really an old idea, but it's getting very trendy these days, and it's getting a lot of attention these days because it turned out to solve a lot of problems that in machine learning. Like one difficulty that I had when I started machine learning is that you have so many algorithms. Which one are you going to pick, right? It's very hard to figure out based on your domain, your problem, the algorithm to use. But it turned out that actually neural network can help because solve a really broad series of problems. So it's quite nice to have a tool that can solve several problems. However, how does it work? It still feels a bit like magic, like a black box. Because there are a lot of nice tools out there, like, you know, TensorFlow is one of those, like Python and Tech, yes. Microsoft come out also with C and Tech and so forth, and they're pretty cool, they works, but it's not that sexy, right? You just get the data, you clean up your data, be sure they're okay, and then you push in these tools, wait for the output, and most likely it works, but how that works, right? So I'm the kind of guy that I want to understand, or I want to open the box. I want to see, you know, what's going on inside. So I decided that the best way to understand how work neural network is most likely implement one yourself. So there are definitely actually many different kinds of neural network, right? Depend also what you try to achieve. There is we're going to take a look at two in particular, but like there is the forward, multi-layer forward. We're going to see that you use for prediction. The recurrent neural network is the one mostly using in natural language processing when the neurons are going to feed back itself. If I use some term that you're not familiar, like neurons and connections, so forth, don't worry. I'm going to build up. You're going to be familiar with this term by the end of the talk. So there are, as I mentioned, there are different neural networks. We're going to focus on the multi-layer feed-forward, which is not really one of the easiest, but is probably the easiest to explain and to work with. And I really like because it's the one used for prediction. So you can play like in financial, get rich eventually. And the self-organized maps also for optimization, like one of the problems that can be used to solve is the traveler cells problem or the study of DNA sequence. And I picked these two in particular because the multi-layer forward is supervised, rather in a position, the self-organized map is unsupervised, okay? So the main difference between the two is that when you have a supervised neural network or machine learning algorithm, you have a series of input and the correlated output. So in this way, you can train your model, and we talk about this word training and model, but then when you train your model, you send some input, and you can compare to the desired output and adjust the value of your algorithm, right? So you make your model more predictable. And instead, unsupervised, of course, doesn't have any data, but still needs some training, right? And actually, the self-organized map pretty much is able to self-train itself. So it's pretty cool. So as I mentioned, computer perform many operations faster than human being, but faster is not always better, right? For instance, one problem that still today computer cannot solve easily is like, for instance, recognize what kind of picture, right? Maybe the animal in the picture, right? If you have two images, it's easy for you to recognize which one is a cat, which one is a dog. But for the computer, still, this is a very hard task. Like, for instance, you can, divide the image in pixel, analyze each pixel, but what about if some pixel is mixing, right? The image is blurry, right? So this is pretty hard. So that's actually where neural network came to play and can solve this kind of problem quite easily. So if you have any problem that can be answered by one of these questions, most likely also neural network can help you, right? And also can be classified in a classification, like if you're looking for something to group together for some feature that are common, some commonalities. Prediction, as I mentioned, is something that you want to predict for future. Like if you have a series of time-based data, right, the neural network can eventually study this data and predict the coming value for the future. Anomaly, something strange is weird, probably in images. That's also used in a medical field. Clustering and optimization, also that one I mentioned for the self-organized map. And also can be separated, maybe it's hard to tell, but the first 4 are supervised and the last 2 are unsupervised kind of machine learning. And the network is pretty wide used in a different kind of field, but like healthcare, financial, as I said, but these days, for good and bad, it's quite used, like for instance, self-driving cars that need to predict and make decision almost real time, right? This is all based on neural network. Any questions so far? Okay. So this is like the basic example, right? So we're going to build up and start from easy to something more complex. But in this case, in this slide, we have a series of variables, right? and we try to predict something that we don't know. In this case, we have a list of students that based on the grade, the GPA, the age, and the gender, you can predict what kind of sport they can play, okay? So in this case, the last row, we are looking for to figure out what kind of sport the student can play based upon this variable, right? So, and neural network is able to analyze this characteristic and aggregate the commonalities and to predict what kind of sport it's going to play. One thing I want to point out, the first gotcha, probably one of the most complex things to do in neural network is something called normalization, right? Normalization, the act when you try to convert some input in a meaningful way that computer can understand, right? For instance, age, you have a number. It's pretty easy. Most likely you're going to squash and make something a bit easier, but is a number easy to understand. But you have something like a gender, well, that starts to be more, complicated because the first thought you may have is like, we're going to be like 0 and 1. But 0 doesn't have any meaning, right? So most likely going to be -1 and 1. And so for more complex also, input can be like the month over here and so forth. So normalization is something that something important to take care. And there's not really any particular rules, so it's really up to you. Some different kind of try. So what is a neural network? Well, think about a neural network as a collection of interconnected neurons that compute and generate chemicals, electrical impulse, right? And artificial neural network attempt to really to replicate what, in a simplified form, what the brain does, the biological brain does. And because a network try to simulate the brain, they try to solve some problem the human tend to do quite well. So for instance, back to the example of the two images, right? You're most likely able to recognize easily if one image is a cat and one is a dog. And I like this quote here because it said that really machine learning is algorithm that self-adapt, really as a flow in the input coming in. So we're going to see how we're going to train neural network, create your model, but the great thing is that neural network keep learning, right? Keep better as it works. So when you think neural network, who is old enough to remember this, right? Right? So, well, this was, the first, my idea when I thought about neural network, but most likely you'll think something a bit cooler, right? The TX-800 Terminator. And the idea that really is able to make decision real time based on the environment to hit the target, right? Depending of the kind of enemies in front, and the weather condition and so forth. So how this is possible, right? Well, is the continued evolution. Think about when you try to learn to play soccer, right? Well, you go to the field, get the ball, try to play a little bit, kick, and look at the player how they do it. So really over time getting better and better until you get faster, able to dribble, kick some corner, until finally reach your goal. All right, nobody get it, okay? All right. All right, so it's really about the evolution over time. So the biological neural network is really, as I mentioned, is this system of interconnected neurons that transmit electrical pattern, right, these signals. And there's the dendrites that receive some input signal, and based on those input, it fires signal via axon to reach the other neurons. And basically, really, this input are received from other sources, and then combined in some way to perform some operation result. And biologically, it creates some chemical heavy. The neuron become chemically heavy, and then when it reaches some sort of weight, you're going to fire up and send the impulse to the next neuron through the axon terminals. And we can represent, we can try to replicate the biological neural network in an artificial way, right? In this way, we have neurons that are organized in a subset that are called layers. So, and where all the neurons in one layer are connected to all the neurons to the following layer, right? For example, in this slide, we have a 3 neuron layer, 4 and 2. Usually the first layer, we never really count as a layer because the input, just dummy. So this is actually most likely a 2-layer neural network. And each neuron, in this case, has an arrow that's called connection. They point to the next neuron. And the connection has some property is called weight. That is some value that pass to the following neuron. All right, so how does this work? Well, first of all, there is not really need of any really deep mathematical background. There are some matrix operation, can be like linear or multidimensional matrix operation, but really neural network usually are designed as a mathematical structure, but they don't really need any huge knowledge in that. We're going to talk about something called activation function, which is just based on linear algebra, and that's pretty much what you need to know to build your own neural network. Okay, this is start to be probably the 2 or 3 more important slides of all the talk. So any questions so far? Okay. So this is a 3-for-2 neural network. So the blue neurons are the input, in this case 1, 2, and 3. As you can see, they're connected, each neuron connected to each neuron, the green neuron, or the next layer. And the connection is this arrow with is carry a weight, okay? So let's see a bit in details here. So it's hard to tell, but it's kind of weird. I have like a long arm there, but anyways, each in this case, the arrow that go from neuron 1 to the green one is called like sequentially. In this case, it's W0, 0, and the last one probably going to be W02, and the next layer going to be W1 because the next layer 0 for the first neuron. But anyways, when you pass the input, each input is sent to the next neuron. When the green neuron receives all the input from the previous layer, is fire and do some computation. This is why it's called forward neural network, because all the neurons connected to the next one. However, so what is important here is that the green neuron to fire and to receive all the input from the previous layer. So, and then when it's fired, you calculate the sum. If you cannot see, it's just the sum of the product of the input by the weight. So in the case for the first neuron, we have the input 1, and the weight is 0, 0, 1. So it's going to be 1 times 0, 0, 1 plus 2, the second input by its weight. The third input times its weight, and sum all this is called dot product, plus a bias, which is a constant. We're going to talk about the bias shortly. And apply this activation function. And we're going to see also what is an activation function. So pretty much this is what you need to do to calculate the output that is applied to the neuron, the green neuron. And the same thing applies also to for the next layer, right? All the green neuron calculate this value that is sent to the next neuron, the orange one, and apply the same exact functionality, right? Dot product of the input by the weight, append the bias and activation function. So what is important here, we talk about weight and bias. So the input we're just passing the input, so we know what are the inputs. The weight, where they come from, right? But there are 2 options here. When you start to create a neural network, well, you don't have the weight. You have to create a model. So in this way, the weight are completely a random number. Actually, a random generator they apply for you this value that can be from -1 to 1, okay? And this is the process of training the neural network and calculate the error and then apply this adjustment to the weight that over time update this weight. So when you start, for instance, from the weight of 0, in this case, the weight is, the first weight is 40, right? Well, when you apply in the end, when you train the model, this is going to be a different number. Then, when you're done with this process, you will most likely save this model. So next time you don't need to train neural network. You already have this weight, okay? So you start random, and in the end, you have this value you're going to save and persisted. So you're going to load up in your model, I mean, the neural network, you'll load up in the neuron, okay? This is very important. Any question about this part? This was really this more important thing of the neural network. All right. So we talk about the first 3 steps, A, B, C. Then there is the calculate error and update weights. I'm going to talk about that in a second. So, yes.
The activation function, is that happening inside that green node?
Yes, is the last step. So To calculate the output of each neuron, you have the sum of the weight and the input, then you plus bias, the appended bias, and then all this sum is going to apply the activation function. Yeah.
But it's a process that's inside
Yeah.
the brain.
Yes. Each neuron calculates exactly the same thing, yes. So the bias is something that can create confusion sometimes, but it's just a constant, right? That you add to the process. For instance, if you have like a linear equation, right? Most likely in a Cartesian plane, most likely it doesn't start from 0. It starts from some value, right? It can be 1, 2, or whenever. The bias is always that constant, and most likely you can treat the bias as a weight. It can be updated. So there is in the community there is some some conflicts say this should be never changed. Others should be treated as a weight, but I treat it as a weight, and it's fine. So activation function really define the value that is propagated to the next layer, and the purpose of the activation function is scale the output in a meaningful and a proper range, right? For instance, we have different kind of activation function. The sigmoid is the most used activation function when you have like to perform a classification between two dependent variables. Most likely you have to predict the gender, it can be male or female, right? And the output is always a number between 0 to 1. Then we have the hyperbolic tangent function, which is best choice for hidden layer, the layer in the middle of the neural network. And they produce the value between -1 to 1. And then we have the softmax when we have dependent variable to compute that there are 3 or more. For instance, if you want to calculate the political dependent from political favor for opinion like liberal, Democrat, and so forth, you have multiple values, right, to calculate. And the output is a series of values that can be 3 or more, but the sum of these values is going to be 1. And the higher value most likely going to be your desired output. And this is actually pretty easy to implement. You go to Wikipedia and you can just implement it quite easily yourself. All right, so this is a LBO code here. This is like C#, C, C++, any sort of C languages. But again, don't worry about the language. Just to give you an idea how the traditional neural network is implemented, which is array-based. And the code is inside this square here. We see is a bunch of for loop and nested for loop that access the value in this array and apply what we just saw, the sum, the product sum of the input and the weights, then apply the bias, and then the activation function. And this is for the hidden layer. It's hard to tell from the folks in the back, but for instance, you have the H sums, stand for hidden sum, and then we have the O sum, which stand for output sum. And the same thing applies also for the next layer and so forth. So it's really for each loop to access the array and update the value. So this is like the traditional way. However, I found that myself is a bit complex. I would have like a piece of paper, a pencil, to be sure that I match the index. So it's not really easy task to implement for me. But I figure if you see actually, I will implement in an easier way. So we talk about neural network, but when you have a model, you start with a random weight. Something important to apply is something called training, which is the process actually figure out the weight of the value that produce and better performance your model, right? So really this cycle that update your weight until you reach your goal. And there are several techniques you can apply. The most common one is called backpropagation, and which is called backpropagation because I have to wait all the output as computed to calculate the error and calculate the delta to apply to weight, and then go backward to each neuron and update the weight. So that's why it's called backpropagation. There are other kind of training. I implement the particle swarm. These days they say particle swarm have a better result, but it's slower to train, take more time. I have still better result with backpropagation, but so usually when you train a model, you have this well-known set of data. And what you do, you shuffle the data, you randomize the order, and then you pick some sort of 70% or 80% of data used to train, and the remaining one to test, right? Actually, if you get something that computes correctly. And then we calculate your accuracy. And then when you're done with the first training, actually, if it's not accurate enough, you reshuffle again this data, you partition again, and you run another epic, okay? You keep iterating until you reach the accuracy that you're looking for. And the training neural network, we try to minimize the error of the, to modify the weight of the neural connection, right? And the most popular one is called gradient descended, which is kind of buzzword, but pretty much that's what it does. It just calculates the value until it reach the bottom, right, of the equation. So this is like in a ideal world, we use gradient descent algorithm to minimize the error of the function. However, in the real world, this is the minima where we want to try to reach the value. In the real world, it's a bit more complex. There is something called momentum. You try actually to move the value from the narrow part here, otherwise it won't try to find another minima. We're not going to cover that, but actually it's pretty easy to implement. So this is another snippet code, but just to show that the process to calculate the error and apply is just a series of steps. You calculate the gradient, which is the error between the output and the value that you're looking for, and then you start to update again the hidden layer backward from the last one. Any question? All right. So let's start with the fun part.
Is this embarrassingly parallel?
Yes. Yeah, I mentioned it in the beginning. So we're going to touch that because I really want to talk about how we distribute the work across machine. But yeah, it's embarrassingly parallel because we can usually, it's called divide and conquer, the approach that you can get a series of an algorithm that can be split in small subset and then partition the work in parallel and rejoin the result. Okay. So it turned out that actually, if you think about neural network, it's like a functional, it's a function, right? If you're not familiar with functional programming, well, think about a network like it's a mathematical function that accepts some numeric input and generates some output. So really, input, process, and output. And most likely, when you create your model, the output depends only by your input, right? So in functional programming, you have something called function composition. Whenever we have a function that the output matches the input of the following function, you can compose these two functions to create a bigger function, right? So think about neural network, pretty much do the same. When the neuron is this function that create the dot product, apply the bias and functional activation function, while you have the input and the output, and you can compose this neuron as a bigger function. And of course, it'll be more complex neural network because they have different input and different output, multiple input, multiple output, but high level the concept apply. So without going into much detail here, in 6 lines of code, I was able to implement almost what we did in all the bunch of C code with a bunch of for each loop, right? We create a function that it just append a value to a given vector array, which is used in the third line to append a bias, okay? And then the last function, the layer, well, the layer function accept the activation function is input, the weight, which is your model, and then the input and produce the output. And you can see here the last line do exactly the same functionality inside the neuron. Dot product, bias, and activation function. Even better, right now, we can just use actually this line of code to implement our neural network, right? We have the first line, you can see how easy it is to implement, like for instance, a sigmoid activation function. We have 3 arbitrary small here weight, or this could be like your model for your neural network. And then we create like a 3-layer of neural network. We leverage the layer function, passing the activation function, and the the weight of the model for each part, for each function, and then we can use this double arrow, which is used for compose function, right? This is it. This actually we build our neural network, which is pretty nice. So in this case here, we can, if you have actually a list of arbitrary layer, we can create an even better helper function that compose this function. So you're not more like dependent from 3 layers. You can create this function that can accept any arbitrary number of pair of activation function and weight, and create for you a neural network can be any sort of number of layer. And then, of course, you execute it, right? So in this case, you can see that the input of the collection of pair activation function and weight is applied and composed to the second one. The result then is applied to the third function and so forth until you consume all the function and you compose your one. Yes? Oh, this is a F#, right, which is open source. So the source code that I have ran on Mac, Linux, Windows that you download from GitHub. However, I'm not a big designer, so I build on a fly sort of UI that I can show you later from create like a random, let's say a neural network that's run only in Windows, but the code can run any sort of machine, right? And but just, again, languages are not important in the concept, right? You can pretty much apply the same thing other programming languages. It can be more verbose, less verbose, but the same idea to compose and treat neural network as a function, right? So I'm gonna skip this part because I want to do the demo altogether later. So this is gonna be the fun part. So we talk about neural network as a group of nodes connected, right? That sounds familiar? Anybody can have an idea? An agent, right? Different agent. So the agent is this unit computation that agent or actor that are slightly different but can be applied the same concept here. And they're used to parallelize neural network. Actually, is called network parallel training, neural network parallel training, NNPT, yes. In this approach, the neurons of the artificial neural network are divided across machine and cluster, right? So each machine holds a portion of neural network. And then you can start the training and process in a cluster machine in parallel, right? So in this way, think about this unit computation that it communicates only through messages, right? So the agent sends message to another agent. And the agent are put like in this mailbox. So, and the agent, when receive a message, it react and do something, apply a behavior to this message. And it can also have a state internally, which is isolated, which is a great concurrent programming model because you have like 100,000 of agents that run in parallel without, creating any sort of race condition, deadlock, or this kind of concurrent hazard. The state in this case can be the weight and the bias, so we can isolate there. And the behavior is going to be, the process to apply when the neuron receive all the previous neuron inputs, right? Sorry, output. So in this case, the neuron can be treated as an agent that send messages to the next neuron, next agent, and process, right? As I mentioned, yes, is a single independent and isolated unit computation autonomous, right? And communicate only through message passing. And really, we can use the agent to replicate the neuron behavior. And when I done actually some research, I was pleased to find this paper here that talk about how parallelize back propagation neural network, which is actually quite heavy to compute when you have a model, especially in large system, applied to the classes. So I had this idea to model the agent to a neural network, so I figured out not that crazy, right? Somebody else already did it. So in this case, actually this is from this image from the paper. And it explains actually the topology of distributed neural network that you can push on different machines, right? And if you think about it, this is if you want to build Skynet, right? This is the way you want to build it. When you have different machine independent, they all connect actually from the neuron, right? So you kill the mother, you kill everybody. Anyways, so it's pretty cool. And this is the criteria to implement that I used to implement this project. But the main part is that the agent will be able to capture the important complex behavior of the neurons, especially because neuron can change slight behavior depends upon the layer, right? For instance, the output neurons are going to have a slight different behavior than the hidden one, right? Because they don't send message anymore to the next neuron because they are last layer, right? So they send out to the output and so forth. So back to our model of the neural network, we can try to replicate how it works in a biological brain with different layers. If you think about it, the actor programming model really very much is in line with the neural network design, right? Each process that you spawn, the agent could be like an independent subset of the neuron and acts like as intended that interact with the other agent, receive messages, compute the messages, and the messages are just the connection between the neurons, right? This is the best animation ever done in PowerPoint. Very cool. Anyway, so it really match one-to-one, right? And this is a conceptual code, and actually I saw the code later, but the idea is that each neuron have this state internally isolated and protected, which is the connection, which now have two properties, not just the weight. One is the weight, of course, but one also the connection of the next agent, the next neuron, right? So whenever the agent receives all the input, it's going to fire up to the next neuron. And high level, you can really see how the similarity, right? We have the neuron that process the electrical signal over time. Instead, the agent is idle and it reacts to the inputs, right? Whenever you send a message. And the synapse, the connection of the neurons, well, the agent like communicate through message passing, right? We have the dendrites that collect the input and to fire to the next, to fire the computation to send to the next neuron, and the agent that I really in real time update and broadcast to the other agent, right? So this is still F#, but ideally this is the main idea. I alias the neuron, the agent with the name neuron to make it easier. But now when you create a neuron, you just pass your bias and your weight, and the hyper layer have the activation function they're going to pick up. But the idea is that now this bunch of neurons, it can be like 1,000 in your machine because very low memory consumption because it's idle when you don't have anything to do, but it asynchronously wait from this input to connection. And there are two states here. One, when receive a message, it check. If the message matches the number of the previous neuron, it means it receive all the input and proceed with the computation. Otherwise, append the message and wait to receive the next one until you're going to receive all the inputs. And ultimately, when you receive all the input, apply the logic we saw earlier, the same one, the dot product plus bias and the output fire applying the activation function, and broadcast the message to all the neurons. Question? There's a lot to digest for Sunday morning, I know. Probably need a drink, right? All right. Let's do a quick demo that. So this is the source code that you can download from GitHub. However, as I mentioned, to run the UI, you have to run on Windows. Otherwise, you can run just you can create your neural network using this model quite easily in any sort of platform. What is nice here is that it's designed for the multi-layer forward neural network and the self-mapping here, but you can create your own. And what I found interesting that is that now we have this idea that your model start with some neuron, right? And with the original model, when you start with like a multi-array or multi-dimensional array, when we start with your neural network topology, it's hard to add or extend other neuron, right? But in this case, you can add on the fly multiple agent, right, and reduce. So actually, it's quite nice when you test and you create your neural network to achieve a better result. So this is let's make it a little bit bigger. So this is the source code that I was showing a slide, right, which is the neuron that applies some, wait for the connection and apply some functionality, right? We have some UI here, let's start it. Actually, wait 1 second. When you start here, you can set the number of neuron layers. So in this case, I have, fortunately, the projector doesn't have a great resolution, so let's see. Okay, that's better. So in this case, I add a layer with a feed-forward layer, and I pass the number of neuron, which is 4, and I pass the default derivation function, which is a sigmoid in this case. I think I defined before in the code here, and then I add another layer, the third layer, all feed forward with the same sigmoid derivation function here, and it's going to be a 4, 7, and 3 layer neural network, right?
In that function, does that set up the whole monad? Does that set up the whole function?
Yeah. Yes. So when you create a many layer here, and then you create a build called build here, it creates a neural network for you, and now you can just push input to the neural network and create for you. And here I comment, but there are other more complex, like a 5-layer one, and then we have another only 2. But like you can create and play with this, right? So when you create your neural network, there is no any specific rule how many neurons each layer should have, right? It really based on your training. It's based about you keep trying until you reach your better output. So in this case, I have the classic example, the iris set, which is a famous study neural network. What it does, it provides 150 training set ready with input value to determine the type of iris flower based on the color, the petal, whenever. But the idea here is that when we load the neural network here, as a part of the training, we compose in somewhere here, we split the input in 80-20, and we run one generation, actually rerun it. Okay, so you can see here above there is some epic 01, 02, and print also the error. And here are our 4, 7, 3 layers. You see that inside this, I'm not a designer, I mentioned that, right? The color pretty bad, but hey, it keeps updating the values, right? So here I done only 50 epic, and for each epic, actually, it ran what is 120 values against 30, right? And every epic, if it doesn't reach the accuracy that I was looking for, it reshuffled this value and rerun another training, right? So in this case, well, I read it for you for the back, so you trust me. But I ran 50 epic, and the last 20 here, I calculate the expected value with the output, and which is the calculated delta, and then the accuracy is 93.33%, which is okay. It should be better, but again, I ran only 50 epic just for the sake of the demo here. Most likely, in a real case, you're going to run multiple, like probably a couple hundred, probably you change your topology and so forth. And here, like the regression here, to figure out now the dots here are the flower that are put in your as input, and this is the line that represents your output, right? So they're pretty close, quite nice. Any question about this part? All right, so again, download the code here and play with the code and take a look, and let me know if you have any question. However, we have 60 minutes, so I want to fly quickly to the map reduce part, and then the cool part, the map, the self-organized map, will take only 5 minutes, but it's very cool, that part, so bear with me. So first of all, agent was a failure. What do you think? So run locally, add extra overhead in your local machine, of course, so most likely you're going to use the next approach that I'm going to show. But again, if you build Skynet and you want to really distribute the work across multiple machines for a super large neural network, definitely this is the way you want to do it. So why parallel computing? As I mentioned here, neural network is all neurons connecting each other, right? And in this case, we have like about 500 connections. And they can grow quite quickly. Like for instance, if you add 1 neuron you generate 19 new connections, right? So they can explode in the number of connections. So the training, especially, is the more heavy computation, and that's when you try to make it faster, right? Especially if you remember for the previous slide I was showing, there's just a bunch of for each, right? So how are you going to parallelize that? How are you going to make it faster? Well, as we mentioned here, you can consider it like neural network as inversely parallel, so easy to parallelize. However, there are two values that you have to consider. One is the epoch, which, as I mentioned, is the number of the time you're going to run in training your model. And the other one is the learning rate, which affect the magnitude of the delta value to add to the weight, to update the weight, right? So a large value of the learning rate create also a large delta, which adjusts the weight faster, but most likely you won't have a precise neural network, right? And probably it's something called overshooting your weight, right? On the other side, if you use a lower learning rate, well, your model is going to be more precise, but going to take longer to train. Here, just for the sake, the third and fourth line of code actually are the slide that I showed previously, with compute your output and then calculate the error or your output, and the rest of the code apply backward the adjustment of the weight with the delta that you compute. All right, so here we can, just as an idea, you can just parallelize all these for each loop quite easily, especially in the lot of languages that provide this support. And this is actually how general graphic processing unit work, right? You can spawn, like I ran the test in a separate hardware, which is I forgot the name, but it's 192 micros core in the GPU, and definitely from like few seconds to train my model, it was like almost real time, right? But really can parallelize quite easily. And you think about it, the reason is because you can map the neural network design pattern here with something very much familiar, right? We have input, some process, and some output, right? So in each layer represent pretty much your computation. Am I familiar with the MapReduce? Quite popular, especially from Google, that published the paper in 2004. Anyways, it's the idea that we can partition a set of operation in multiple operations can run in parallel, MapReduce, but most likely it's just a MapReduce. In the real world, it can be like filter, group by, again filter, again map. So it can be different kind of steps. But ideally, and this is just I'm going to gloss over, but to give you the idea how you can create your function. In this case, the map function. That this is also F#, just to run in parallel some sort of projection and get some data you pass into it. Your reduce function, okay, also this run in parallel, and then as was showing earlier, we can compose this function together, right? And you remember from the previous slide, when we create our neural network with just 6 lines of code, we compose the function to create your neural network, right? And the same apply here also for MapReduce. So quite easily you can parallelize each step of the computation and to have like lightning fast result. Especially when you run in clustering, when you distribute the work on neural network in different machines, you can parallelize in each independent machine that subset of the neural network. All right, so last 3 slides, and then the other cool demo here. So talk quick about the unsupervised training, right? Which is quite common technique. This is called actually self-organized map. In this case, we're talking about the famous traveling salesman problem. Anyone familiar with the traveling salesman problem? All right, few hands. You just wake up? Good. All right. And the idea is that the neural network is treated as a 2-dimensional map of nodes, right? Actually, it turned out that the traveling salesman problem is used it's not just like a fun algorithm to build, but it's used like in how to determine predict the protein function and DNA sequencing processes, which is quite interesting. But anyways, so I don't know if you see the animation in the back. So at first, the travel assessment problem seems easy problem. I mean, it's easy to solve, right? However, the bigger the number of the city, the bigger the combination you have, right? So you cannot just brute force. Like if you have 2 cities, most likely you have 1 path. That's fine. 5 cities, 120 paths. But if you're like 10 cities, you're almost like 4 million different kinds. So if you're like in this case, the demo thing is like 100 cities, it's gonna probably take years to calculate, you know, the output and the best output. So in this case, neural network provides a great solution, right? We treat neurons as a 2-dimensional layer nodes. And what it does is start a neural network as a ring, actually. And during the learning procedure, it changes the shape of the ring and figure out how to touch the other city and create for you the map. And of course, again, I'm a paper junkie. I found this paper was awesome that say, well, you know, back here you have this algorithm, but how are you going to make it faster, right? Because that's my background. So I say, well, let's try to implement this paper in something that's familiar in code, right? And the approach really divide and conquer the city in section. And what it does is it uses a clustering, which is again neural network, cluster, and group the city in communities, and then apply the same the solution for each community, and then ultimately use something called a blend function, they call it, to put all the solution together, which is quite nice. So let's run the demo here, which is pretty cool. All right, let's close this guy here. Any question? Okay. I'm not going to show the code, but the same idea was building the neural actually as agent and communicate. So the 100 city, we're probably going to create like 150 or 200 city here. There are like 200 different agents. Oh boy. All right, terminate here. No. Let's close it, try it again. Don't give up on me. This actually is pretty cool. Yeah. Okay, it's getting better, it's getting better. Okay, it's loaded symbol. Why loaded the symbol? Okay. All right, cool. Let me make it bigger. We have 100 city, 25,000 iteration, and we have 400 neurons, right? So how does this work? Actually, this model creates 1 layer of 400 neurons, which is quite large, right? So let's build actually, let's put like 150, and let's put like 700 neurons, why not? Initialize, so I have more city here. Let's start with the classic approach, right? So you can see it spawn all the line, and then you start to find the best solution. I have iteration that's getting better and better. This is self-training, okay, right now. So you figure out how to touch the city and adjust the path on a fly. So this is quite nice. But of course, this is can be parallelized. So let's make 2 clusters. This took like 6,800 milliseconds, okay? I put 2 clusters here. Let's start with the traditional, well, the parallel way that split the work in 2. You can see, okay? And then use the blend. It took 2,600 milliseconds, which is less than enough, right? Let's make 4 clusters here. Okay, it took 1,200 milliseconds. The blend function is not perfect there. Sometimes work better than other, but you know that's how I interpret the paper. However, what I want to show here, what is interesting, let's initialize. Let's put 0 iteration here. So the traditional way that work at 0 iteration is really 0 iteration. Okay, at 0 iteration, it really threw on a map a bunch of lines. Okay. And from there, I try to remove what is not correct, right? 0 iteration, a bunch of line. 1 iteration got better, and so forth, right? However, the self-map organized work in a very smart way. In this case, it creates a 0 iteration. I put 0. It creates a circle, okay? And try to figure out how to touch the city in this map. With 1 iteration here, it's going to change the shape, like oval. It's going to be one side going to touch one city, okay? And then the second iteration here is going to be on the one of the other 3 sides of the circle, try to find another city. Well, that's not really usually. But anyways, so let's go 3 here. So very much different kind of strategy how to apply between the two approaches. Like one use a neural network, one use k-means clustering here. So that's pretty cool. Any question about this part? I recommend actually to read the paper. I'm also almost over time. Actually, I'm over time. So what I want to show here is just the link where you get the code. The takeaway just is awesome. That's all I got. This is the link where you can get my information here. Actually, the source code, there are 2 versions. One is in workshop. You can download it. Actually, you can follow the step to build yourself a neural network. And the other one is a complete solution. So if you can play, why not? But question? I know it was a deep talk for a Sunday morning after a big party last night. But I hope that you enjoy it. Probably take home some good information and motivated to try and build your own neural network, which is not that complex. All right? Yeah.